Consider, if you will, a beaker of 10th molar nickel nitrate and a beaker of 1 molar nickel nitrate. You can tell that the concentration of this beaker is more because the characteristic green color of the nickel ions is darker here. And what would happen if you mixed those two together? Now, hopefully some of you are thinking, oh, I would just get a larger volume of half molar and nickel nitrate solution because you mix them and the concentration would change. You would almost be right. What you actually get is a 0.55 molar nickel nitrate solution. So assuming these were equal volumes, the average of 0.1 and 1 is 0.55. So anyway, you get, you mix them up and the concentration is, in between the dilute one and the concentrated one. Now here's the actual question. Could you accomplish this concentration change without physically mixing the solutions? And what I mean by that is an end state where, let's say that this was 100 milliliters and this was 100 milliliters. So in this case, if you physically mix them, you get 200 milliliters of this 0.55 molar solution. Could you end up with 100 milliliters of 0.55 molar nickel nitrate in the one beaker and 100 milliliters of 0.55 molar nickel nitrate in the other without mixing them? So, you can't just mix them together and then separate and split them back up again. That could you actually achieve this concentration change, this one increasing and this one decreasing without ever physically mixing the solutions? So hit pause and think about it. Now, obviously, the idea is that if I propose this fairly insane thing, that it must be possible. Here's how you do it. All right, you make a cell, and so this is my hastily improvised cell bridge here. So you've got the nickel solutions here, and what you do is you add a cathode and anode, both of which are nickel metal, and connect them. And if you would let this go, believe it or not, you would end up with two beakers filled with 0.55 molar nickel nitrate solutions. And how does that work? Well, so here is the proposed reaction for the cell, right? Now in this case, and in this cell, you need to increase the concentration of nickel ions from the 0.1 to the 0.55. So this is the oxidation, this is the anode, the oxidation cell, where the nickel is becoming nickel plus 2. Now in this cell, what you would need to do is reduce the nickel ion concentration. So this is the cathode, or the reduction cell, where nickel plus 2 becomes nickel metal. Now, what is the standard cell potential? Well, clearly it's 0. So the reduction potential for nickel is negative 0.25 volts. The oxidation potential is positive 0.25 volts, giving you 0. But this is not a standard cell, right? This is a standard concentration, but this is not. So this is kind of what we just did before. So let's see what the cell potential would be at this instant with 1 molar nickel nitrate in the cathode cell and 10th molar nickel nitrate in the anode cell. All right, so here we go. So the inertia equation to the rescue. And here our standard cell potential, as we previously defined, is 0. This is a 2-electron process, and we still have a factor of RT over F here, just times the natural log of 0.1 over 1. Now, this is going to be, this natural log is going to be a negative, it's going to be a negative number because this is a number that is less than 1, which will make this expression positive, which means it will have a non-zero and, more importantly, a positive cell potential, which in this case is a mind-whopping 0.0296 volts. All right. But so let's think about it again. So that means that this reaction, this cell is spontaneously reacting, not by much, but it is. So again, let's analyze what's going on in this cell here. So in the left-hand side, we've got nickel becoming nickel plus nickel becoming nickel ions. And whoops, there's a mistake here. Let me fix this. So we've got 2 electrons here. And in the other cell, so this is the oxidation cell or the anode. And on the other side, you have nickel becoming, same mistake here, reacting with 2 electrons to become nickel metal. And this is reduction. So the question is, what on earth is useful about a 0.0296 volt battery? And the answer is, this is incredibly useful, because you could suppose that, let's say that the nickel in the anode cell, the nickel metal, is not completely pure. Now, assuming that the impurity does not react in this system, and you could design it like that pretty easily, what happens as the, so remember that this is the anode, so basically this metal is, this metal electrode is losing mass because the nickel atoms in there are becoming nickel ions. But as that happens, consider what happens to the impurities that would be trapped in there. Well, you have impurities in the nickel electrode, and they would just fall to the bottom. Again, as this anode kind of reacts away, the impurities just sort of settle to the bottom, again, as long as they weren't reacting with everything else that's in here. And then what happens? Well, those electrons, transfer here, work their way here, and the nickel cathode increases in mass. And this is actually a way of purifying nickel, because what you end up here is that these impurities sort of fall to the wayside, and the nickel metal that builds onto here is actually quite pure. So this cathode builds and is an increasingly large and pure piece of nickel. So these concentration cells are how a lot of metals are purified, specifically copper. So when you refine copper, it ends up being not that pure, and this is what is called blister copper. And these are set to be the anode in a concentration cell. The cathode is, the cathodes start out as small pieces of very pure copper and end up as larger pieces of very pure copper. Again, and this can be done essentially without supplying electricity to it. So this is a neat way of purifying metals. Notably, copper is purified this way quite a bit.